Hi, I'm Mike Danielchuk, and I'll be presenting our joint work between the Auto Lab at UC Berkeley and robotics at Google on a novel robot mechanical search policy for efficiently extracting a target object from clutter based on minimizing support of learned occupancy distributions. When operating in unstructured and semi-structured environments such as warehouses, homes, and retail centers, robots are frequently required to interactively search for and retrieve specific objects from cluttered bins, shelves, or tables, where the object may be partially or fully obstructed by other objects. We consider a setting of this mechanical search task where the goal is to extract the known target object from a heap of objects, as shown here, in as few actions as possible. Previous work on robotic mechanical search has focused on learning joint, pushing, and grasping policies for operating in block scenarios, learning continuous pushing policies to uncover a partially occluded object, using shape completion in volumetric memory or a particle filter for inferring target object whereabouts, and using a hierarchical policy to iteratively remove objects. Typically, these policies operate directly on RGBD image inputs while leveraging segmentation and other object detection methods. Leveraging recent advances in object pose prediction and gaze prediction that predict distributions over object poses or gazes, we aim to instead predict an intermediate representation that encodes a distribution over target object positions in a heap of objects. We term these distributions occupancy distributions, since they represent the unnormalized likelihood of each pixel containing some part of the target object. In the case where the object is partially occluded, the occupancy distribution collapses to the amodal segmentation mask of the target object. However, in the case where the object is fully occluded, the occupancy distribution encompasses all the amodal segmentation masks that could correspond to object locations leading to the same RGBD scene image. Intuitively, if there are many possible positions of the target object that are consistent with the observed RGBD image, then the support of the occupancy distribution will be large. However, if this is not the case, then the support of the occupancy distribution will be smaller. We build the X-ray mechanical search policy on top of these occupancy distributions, where the policy aims to maximally reduce the support area, or the number of non-zero pixels, of the occupancy distribution at each time step. In the case where the target object is partially occluded, this results in the policy grasping the sunscreen tube that directly covers the target, revealing it, as shown here. However, when the target is fully occluded, the policy grasps the mustard bottle as it reveals the largest amount of space that could contain the target object, as shown here. In this project, given an image of the target object and an RGBD image of the heap, we wish to estimate the occupancy distribution for the target. Our approach is to learn this function using a fully convolutional neural network and train it entirely with synthetic images. We develop a dataset generation process to efficiently learn to predict the target object occupancy distributions. We generate heaps of objects first by dropping a target object and then sampling a set of objects from a larger set of 3D object models and dropping them on top of the target object using PyBullets dynamic simulation. We wait for the objects to settle and render an RGBD image of the heap. We also render a modal mask of the target object and combine it with the depth image to form the input training image for the heap. Here, the target object is not visible, so the modal mask for the target is blank. In this case, the modal mask contains a sliver of the target since it is partially visible in the input image. Then, to generate the ground truth distribution image that corresponds to the given input image, we rotate and translate the target object in the image plane and check to see that if a specific location for the target would lead to the same modal mask. If it does, then we add the amodal object mask for that translation and rotation to the occupancy distribution. In this case, any location for the target that results in a blank modal mask is added to the distribution, while any location that results in a modal mask with some non-zero pixels is not added. We stride these rotations and translations across the image and aggregate amodal masks to form the final distribution. When many image plane translations and rotations for the target object are considered, for example, we use 16 rotations and 3072 translations of the target object, we get a smooth distribution over pixels. However, the previous method only considers a single target object. The occupancy distribution for a different target object hidden in the same heap can dramatically differ, as shown here, for rectangular target objects of various aspect ratios. Additionally, we wish to scale this occupancy distribution prediction to objects that are unseen in training. We find that the geometric property that most influences the occupancy distribution for unseen objects is in fact the aspect ratio. Thus, we train a series of decoders for each aspect ratio, and at test time, we simply choose the aspect ratio that most closely matches that of the target object. Specifically, while training, we output a 10-channel image where each channel represents the occupancy distribution for a given aspect ratio. Then, we only enforce loss on the channel corresponding to the aspect ratio of the ground truth target object distribution. The trained network predicts the occupancy distribution in about 6 milliseconds, which is over 250 times faster than the ground truth calculation. Then, during testing, we choose the output channel that most closely matches our target object unseen in training. For example, the lid object shown here most closely matches the 1-to-1 aspect ratio. We also scale the input image according to the scale of the target. For example, here the image is zoomed out by a factor of 2, since the target object is about twice as large as the training object. We show performance of the network on a set of heaps and target objects unseen in training. We find that the network can accurately predict occupancy distributions for novel objects such as the lid, domino, and flute shown here, although it occasionally includes spurious predictions as in the last row of images. We also evaluate the performance of the network channels that are mismatched with the target object aspect ratio, such as evaluating the 5-to-1 channel on the lid, and find that in general, channels for smaller aspect ratios such as 1-to-1 or 2-to-1 tend to overestimate the distribution for larger aspect ratio targets. However, channels for larger aspect ratio objects perform relatively consistently across different aspect ratios, even ones that are much smaller. We then leverage our learned occupancy distributions as part of a mechanical search policy. We can express the general mechanical search objective as an optimization problem where we try to find parameters theta for a policy pi that maximizes expected reward over a finite horizon, corresponding to extracting the target object in as few actions as possible. In this setting, we receive a sparse reward only when the target object is grasped. In this paper, we instead optimize a denser reward that can be calculated at each time step. Namely, we take the action that greedily reduces the support or number of non-zero pixels of the occupancy distribution. We hypothesize that optimizing this dense reward is similar to optimizing the true mechanical search objective, since we aim to take actions that continually reduce uncertainty of the target object's location until it is finally uncovered and can be grasped. This diagram captures the full policy pipeline, where at each step we predict both the target object occupancy distribution and segmentation maps for the heap. The robot then removes the object mask that contains the largest amount of the occupancy distribution. Scores for each object are simply a sum of pixels in the mask weighted by the occupancy distribution values. Here's an example of a simulated policy rollout. The policy is intuitive. It grasps larger objects that include large regions of the heap when the object is initially unseen. Then, once the object becomes partially visible or the distribution collapses, it focuses on objects that directly occlude the target. We compare the proposed policy to two baselines introduced in previous mechanical search papers: a random policy that grasps the target if possible and otherwise grasps a random mask, and the largest policy that grasps the target if possible and otherwise grasps the largest object mask. Here is an example of which object mask each of these policies would plan a grasp on for a given scene. In 1,000 simulated rollouts of 15 object heaps per policy, we find that the X-ray policy outperforms all baselines, succeeding in extracting the target object within 10 actions 82% of the time, as compared to 67% for the best performing baseline. In successful rollouts, the X-ray policy extracts the target in a median of 5 actions. The full histograms across all rollouts for each policy are shown here. Similarly, in 20 rollouts with 25 object heaps on the physical system, with a Photo Neo Foxy depth camera and ABB Yumi robot, we find that the X-ray policy again outperforms baselines, extracting the target object 100% of the time in fewer median actions. We find that the X-ray policy synergizes well with the concurrent segmentation of the scene. For example, under-segmenting and over-segmenting problems are reduced, as they can be mitigated by the weighting of the masks with the occupancy distribution prediction. Here, we show 2 rollouts of a nearly identical heap to express the difference in policy behavior when the object is slightly visible versus when it is fully occluded. When the object is partially visible, the policy immediately grasps the object that directly occludes the target, increasing efficiency in extraction. We also show a full rollout from the physical system where the robot quickly extracts the target object. Color images of the scene from the robot's perspective are overlaid with the occupancy distribution predictions and object mass scores on the left. While we see this work as another step toward successful mechanical search, there are still some limitations of the approach. Namely, this method only considers target objects that are relatively flat in their translations and rotations in the plane. We hope to extend this method to shelf or cabinet-style environments that must take into account out-of-plane rotations of the object, and grasps may be constrained. We also hope to begin incorporating semantic information and memory into the system to further increase extraction efficiency. In summary, we contribute X-ray, a mechanical search policy that maximally reduces learned occupancy distribution support at each time step, and a dataset and dataset generation method to learn the occupancy distributions. We show in both simulated and physical experiments that this method can outperform previous baselines, increasing efficiency and success rate in the mechanical search task. We look forward to discussions and collaboration. Please reach out to us with any questions. Thank you.